I can have your attention, please. All right. Welcome to this fall workshops. This is CAD Principles. My name is Brendan Rockwell.
My name is Sam Calvert.
And we're going to talk about CAD Principles. So starting off, just an overview of who we are. My name is Brendan Rockwell. This is my fourth year at FRC, and I'm the design lead on Team 1678.
Hi, my name is Sam. This is also my fourth year on 1678. I'm on the design sub-team as well as the lead of the Impact Award sub-team.
So during this presentation, we're going to be talking about what is CAD useful for. We're going to go into CAD organization. Just a warning before we get into everything. This presentation is focused a lot around Onshape. It's the program that we use. It's the program we've used for a long time. It's the program we're most familiar with. A lot of these lessons are applicable to other programs. However, we do not have as much experience with that, so I cannot say for certainty that everything that we're talking about is applicable for every software. All right. After that, we're going to start talking about CAD organization. So it's going to be talking about how to store your files, how to put your parts in certain places, most of all to avoid load time. After that, we're going to talk about the CAD process, specifically mechanism design, our CAD standards, and principles that we use to help improve our process, and then the CAD and manufacturing.
So first off, what CAD is, obviously it's computer-aided design. You've got different programs like Onshape, SolidWorks, Autodesk, and essentially it's just a way to visualize your design before you spend a lot of your resources, including time, to manufacture or assemble it. And why does this matter? So in order to develop and advance robots, CAD is essential because you can check for interferences, you can make custom parts and gearboxes, you can do 3D modeling, and you have vital generation.
Yep. CAD is pretty much the cornerstone of everything that we use on our team to create the robots that we do here. So this is kind of a diagram that illustrates just how widespread CAD is throughout our robot process. It's part of our original conception, starting out with the original rough sketches that basically say, will this idea that we have work? Then we go into our actual design, where you stuff like just your sketches, your extrudes, stuff like that, but also your assemblies, your part studios, and then FEA if you want to get really fancy with it. You also use CAD for a lot of your development. So almost all of your rapid iteration is going to be done through CAD to cut things on a laser cutter or anything that you can use to get parts out fast would likely be controlled by a computer. And so you need to have a CAD file for it. That goes into our manufacturing and also our validation. So through assemblies and stuff like that, we validate the ideas that we put into CAD and make sure.
Also, we'll be covering a lot of different topics throughout this presentation. So if you have any big questions, feel free to ask them after we finish talking about a slide, because other people may have similar questions, or if you want to know about specifically what we're talking about at the moment, that would probably be more useful than asking it at the end. So now we're going to talk about how we found the best way that we found to organize our CAD. So whenever we create a robot, we always have a top level assembly. So when you look in here, everything is labeled by a number. Our 000 is the top level assembly. It has every single part of the robot that we've designed. And then after we have our 000, we basically split apart the robot into separate subsystems, such as the intake, the shooter, whatever you have during the game. Because this can make them completely independent of each other, because this not only decreases load time by splitting apart everything in your CAD, but it also incentivizes more group projects and splitting up the work. And very important, we stress minimizing load times a lot, because if you're using a cloud-based service like Onshape, then if you have a lot of people working on a giant robot, everything's gonna slow down to a halt, and you're gonna get nothing done, even if you have amazing CADers, you essentially will have nothing. So.
Also talking about stuff being completely independent, you really want to make sure as much as you can be independent. Even if you think that, especially on a cloud-based server like this, even if you think that having one part in context isn't going to increase load times a lot, because the server is having to go from one document to another, if that other document still has high load times, you're just increasing load times even more. So as independent as it can be is much more optimal, especially for cloud-based servers, but also for something like SolidWorks and things like that. Also talking about division of labor, this is kind of another minor piece of optimization that we still found really important. On your team, you're probably going to have limited, really experienced members, and you're probably going to have other less experienced members. So it doesn't really make sense to have your most experienced CADers spending their time doing a bunch of shafts or a bunch of standoffs or stuff like that. And instead, you can delegate that out to other people and have them gain experience in CAD gain more time with the program and gain a lot more confidence for when they end up stepping up and doing a lot more of the development themselves. Also, a common problem when people are working on a subsystem like this and they're working in a group is a person such as myself last year can tunnel vision in on one thing. And while that might be very nice for me to do, it ends up creating a choke point because when I am spending all my time doing small detail parts, it means that I can't get out bigger plates that we need for stuff like assembly or interference checks or something like that. I can't get those parts out because instead I'm doing something like this, which while on the short scale or in the short run doesn't matter that much. And so I can give that to someone else to maybe do the exact same part, but even if they do it a little slower, it is still more efficient for the team, for the less experienced members to do the smaller tasks, both to gain experience and confidence, but also because it saves time and gets more things done.
And in the past, when we've had like an incident like somebody just did like the entire intake themselves, and because they focused on like doing everything themselves, not delegating, they ended up forgetting that to like space out like a pulley from just a giant piece of polycarb. And when it started rotating like really fast during the game, it basically melted into the polycarb. And we just replaced like the whole side of like the intake because they just forgot to do very basic things, which is why we emphasize like dividing the labor and making sure everybody has it.
A question on that. Do you CAD as a group, like during your team meetings, or did your members like do the CAD work at home on their own?
Absolutely. So the advantage of Onshape, especially as a program for us that we found, is that people can do CAD, yes, at meetings, but also at home. So we try to do as much at home as we can because when you think about the time that you have, you're going to spend more time at home than you are at your shop. And so you want to be getting as much done at home as you can so you can spend your time at the shop doing only shop-specific things like putting together your robot, cutting parts, stuff like that. So we try to emphasize as much done at home as possible. But the disadvantage of that is that you have less eyes on it because you're working alone. You're not working with as many other people around you to say, hey, can you look at this? Does it look right? So we try to emphasize the division of labor on top of that because of the fact that A, people are at home so they can do it better because they have their own Wi-Fi and they're not relying on school Wi-Fi, but also because it gets more eyes on. Any other questions? Oh, yes.
So often with the various parts that you guys delegate out, do you guys divide it into like smaller subsystems themselves, or do you guys even do that to like it's a gut subsystem in the shop that you guys are talking
Well,
about?
if you go back to the slide.
Oh, yes.
So basically, like when you look at each subsystem, usually each of those is like led by a more experienced member who can like outline the whole thing. They'll handle like a lot more like the plates, geometry, and like where like the big like pulleys or like the gears are going to be. And then a lot of like the smaller parts that maybe you don't like if someone's not as experienced, they can handle like different like spacers or standoffs or just even like smaller plates are usually done by the leader. So there was like some division of labor like within the subsystems.
And on top of that, it's also really great because we found that as much good as large scale presentations like this one can do for teaching people like the basics of CAD, we found that in order to really get a deeper understanding, it's often more helpful for people to have like a one-on-one, maybe a one-on-two connection with a more veteran member, because the veteran member can devote more time to like explaining things to the way that the person themselves finds more understandable. Yes. Yeah, absolutely. So for parts that have a lot of like entities or stuff like that, we're going to talk about them a little later, but basically the short explanation is you want to do those as far to the back as possible. Onshape has a feature called the rollback bar. I don't know if you guys have used it before, but it basically lets you go before a thing. So if you keep your rollback above those really high entity parts as much as you can, you're going to minimize the amount of filters and stuff like that.
And then you can also put it like in separate part studio, which helps with it.
It's like really bad. That's something. Like for example, last year we had 2 years ago we had a massive spur gear, and that alone took 5 seconds to load or something. And so we kept that in a separate assembly, built everything else but it, and then in the actual open.
How do you guys organize your modeling goals based on the
On a weekly basis, most of the modeling goals are going to be led by whoever's in charge of like each individual mechanism. We currently have a project management whiteboard created by the lovely Steve Cohan at the back, who has basically enabled us to set specific goals for each week. So we basically establish where we want each subsystem to be at a point, and then after that, we can use that to divvy up smaller tasks by the subsystem. Yes.
Do you have a person whose job it is to make sure all the different parts actually fit together?
Yes, so that is done in part by all of the subsystem leads, but also by me. So as a design lead, my job is to go through the O100 and make sure all of the different subsystems are fitting together. Anything to second?
So now we're going to be talking about sort of like the principles of mechanical design. Obviously, because this is just like an hour-long presentation, we're not going to be like going in depth on like the technical CAD of like every single possible subsystem. This is more like how we like to outline everything and sort of like brainstorm how to approach any mechanism.
So this is kind of the definition that started on our team a while ago. And the idea is that the process of using available resources to efficiently develop a mechanical solution to a series of problems or challenges. So this works for both the robot as a whole, but also for specific subsystems. Basically, this is the task that it has to accomplish, and then from there we work on using what we have to make it work. So starting out, our overall, we're going to start out with a basic idea of what does your robot want to look like. So that is going to be your superstructure. This is a 2022 robot, so it's the indexer. You also want to have a vague estimate of what all your mechanisms are going to do. So it doesn't have to be perfect, but you want to know roughly in what box is everything going to fit. Because obviously, if you don't have a general idea of where everything needs to go, it's going to be much harder for you to actually get a very good understanding of where everything goes before people actually start CAD. Because it's all well and good to check after you started and say, hey, this is going to collide, but it's much better if you can save time by saying at the beginning, try to put this here. And then we also use this to check the feasibility of the design. So for example, this last year we had a bunch of different elevator designs where they varied from a bunch of different things, but we were putting them in a drawing kind of like this one where you're basically seeing, does the extension work? Does the arm work? Or whatever you're trying to do, we were testing and making sure the movement and the overall architecture was actually possible for us to run. And then lastly, again, as I said, it helps subsystem leads understand the interactions. This is really important. When you're having multiple subsystems being designed by multiple people, you really have to make sure those people understand where everything is going to go. Otherwise, you have stuff like an intake ending up halfway inside your index or your elevator, and your drivetrain is going halfway through all of your robots. So it's really important to have everyone understand what goes where and how it interacts with each other.
So essentially, when we just start the mechanical design process, what we do pretty much at the start of the season is like write down what we want each subsystem to do. So for instance, like if we're talking about an intake, we want to talk about like picking up the game pieces. What game pieces are we going to pick up? Surviving harsh impacts, because you can't just like assume an intake is just going to be floating around with like no obstacles in its way, right? Like you're going to be driving it around. There's other robots, like game objects, depending on what they are, like hit it. So you want to be able to keep that in mind, obviously. And then like if we're going off the intake, for instance, then you want to talk about like now we need to figure out like how we want to make the intake durable. Do we want to make it more elastic or do we want to make it rigid? Basically break down like what exactly it is you need the intake to like, fulfill while it's going. It seems pretty simple, but this is like a big question we have sometimes have. Where like if you wanted to make it out of polycarb so they could like bend back and forth, you might have more like elastic durability. Whereas like you could have a more like rigid intake, but then maybe if you hit something it just breaks, it's over from that, right? And then the next thing a very important part of mechanism design when you're comparing up the other mechanisms is establishing the power chain and goal motor ratios. So essentially you want to be able to model out on just a basic sketch of your mechanism and figure out how power is going to get from motors to every part of your mechanism. And goal motor ratios. So, and the next slide talks about more about ratios. So, how to know ratios? We use the expectations for the subsystem and identify 3 things. I guess if you want to go over this?
Yeah. So we have 3 main things that we're looking for in every single power chain that we're doing. We're looking for the goal stall torque, we're looking for the goal motor draw, and we're looking for the goal move time. So starting off with stall torque, this is kind of an easy concept. Each mechanism is going to have to lift a specific weight. So for example, last year on elevator, elevator arm was carrying the entire weight of the robot. So it had to have a really high stall load, which basically means that the gear ratio has to be really steep, so our motor is actually able to support all of that weight without breaking. Next up is goal motor draw. This is really important because unfortunately for us, our batteries do not provide us with infinite power for the entire group of matches. So we have to know what our motor is actually going to take from our batteries so we don't end up browning out in the later stages, but also so if we try to run multiple mechanisms at once, we don't end up just losing all of our power. Lastly is goal move time. This is sometimes the hardest one to figure out what you want, but your general goal is thinking about what makes the most logical sense for it to happen. So for example, for an arm, you don't really want your arm to go from completely down to completely up in 0.1 seconds, because then software is going to have a nightmare with it, but also it's a pretty big danger to other robots in the field, your own robot in the field. You want to make sure that it's going up and down relatively slowly. So instead of having 0.1 seconds, you might want to have it move that in 0.5 seconds to 1%. But for other mechanisms like intakes or stuff like that, you instead want to have your wheels spinning really quickly so they can really quickly intake all of those game pieces. So for 2022, our wheels were spinning really quickly because we wanted to intake those balls as fast as possible.
And also, when you're working on power gens, it's very important that like I would use like if you can find like a third party like tool that allows you to check there are tools that allow you to check torque, motor draw, like move time. We sort of made like a spreadsheet one, but it's not like a super official one or anything. But if you can find that, that saves you a lot of time because you can try like putting in different gear ratios, figure out like what is going to work best for like your idea and like the game you're playing.
It's important to remember that even while you're doing all of this, you still have to think about the packaging. So if you come up with an idea that satisfies your torque, satisfies your draw, and satisfies your move time, but it requires a 20 dp gear that has 400 teeth, you have to start rethinking what you're doing. So you can try to use something like a planetary gearbox, but those can have issues. So you really have to make sure you're thinking not just about how to satisfy these three things, but also how to ensure that you are meeting the packaging constraints of your work.
This is an example of just a gearbox we drew up for some training. So like you can see like the big like hexagon shape is like our motor. Then we draw some like circles to signify gears and just sort of connect them all to create the power gen. And then we would put this all into a calculator to figure out exactly how much stall torque there would be, how much motor draw would be, and how fast like whatever you're connecting to the last gear would be.
And this gray box is also again to represent that packaging to make sure that everything we're doing is fitting within the constraints that we've all set. So now we're going to talk about some of the basic CAD standards that we have, starting from the beginning and kind of working our way up to the phase. So for us, the reference sketch is a mock-up of every single thing that's going to move. Obviously, depending on the mechanism, it's going to vary in terms of how detailed you're going to get, but you're trying to model everything that will move and everything that's really important to how the mechanism actually functions. So for an intake, you're going to model your wheels. An elevator, you're going to model your tubes. And then for stuff like that, you're basically going to pick what makes this mechanism work, and you're going to try to model that. The other important thing is, for example, this elevator, it goes up and down. So this reference sketch has the capacity to move up and down. So you're tracking where in its travel it is, and that's another easy way early on to make sure you're not seeing any passive interferences. If this tube ended up halfway within the top tube, we have to say, hold on, we have to rethink our design. So it's really important to make sure you know where everything is going to move and where everything is going to be hitting or not hitting. The other main thing you want to do is locate major structural elements. So, for example, our 2022 intake had a bunch of bent pieces and tubes that were used to add a bunch of structural support to that entire mechanism. But if you don't model that early on, you might start not realizing where it is in context of stuff like gearboxes or motors. It's really important to make sure that anything big and bulky is also modeled so you know what you're designing.
Here are some examples of reference sketches. It's a bit hard to see maybe from the back, but what we've essentially done here is this was the reference sketch for our intake for the 2022 season. And something important about reference sketches, like Brendan was saying, is like you have to check at them in different positions. We needed to make sure that, because this was like a 4-bar deployable intake, we needed to make sure that it was functional both when it was back like in the robot and when it was deployed. Because if we like designed it only based off where it was like when it's deployed, maybe then we would like build it, realize that it wouldn't fit like in the frame perimeter when we put it back, and maybe if like we designed it about being in the frame perimeter, we would put it down and realize that it wouldn't be touching these like the game objects in the ways that we wanted. So we basically modeled it in 2 different positions for one part, which is a very important part. Like if you have any kind of moving mechanism, you always want to do this for your reference sketches.
And then on top of that, when we're talking about things that move inside of your reference sketch, you can't just talk about like what you're making, you also have to think about how the game piece moves. So if you see in that intake, we've modeled all of the ball's entire path through there. This minimizes dead spots, but also make sure that there's no major collisions with any of our bumpers or any of our shafts or stuff like that. Because if you have that happening, then you need to again rethink your design. And then over here is an example of the shooter. It's pretty similar. You have your big wheel here, your intake or your shooter wheels go there, and you have your gear reduction. But again, the really important thing is this is a slot that is representing the movement of the motor. So you really want to make sure you know where everything in this shooter is going to be going at all times to make sure you're modeling everything that you can. So you're going
Did anyone have any questions about any of like the mechanism design reference sketches so far? So now moving forward, when generating parts, you want to try to have any large load time modifications at the end, which are like we mentioned earlier, because with the rollback bar, you can essentially like go up in versions of like your CAD design and sort of like look at your CAD before you have the massive parts. And another big part of load times is if you use like feature scripts, large patterns, features, you also want to put those at the end. Like for instance, like we use this feature script called the tube conversion tool, where we can just make like a big tube, like click on it, and it just puts a full pattern, hollows it out. But it does increase load times, so we try to minimize that when we can, because like we ended up with like our elevator this year had like a ton of it. It would take a while to load. Stuff wouldn't get done. And then every custom part should be created, but small parts can be separate to reduce load times. You can put them in different part studios, or just import them from other libraries and assembly. If you just want to save space, like in your part studios, so that it doesn't take 2 minutes to load. So you can edit it.
I know we've been harping on about load times a lot. If you see here, 3 parts together putting up like 6 seconds on their own, and there are a bunch of other parts that are putting up similar times below these. So you really have to be making sure that you're trying to minimize those load times as much as possible. Otherwise, you're going to be waiting 1.5 minutes just to be able to make one change. It just happened to us before. So you really want to avoid doing anything that has big load times until it's the very end, and so it's easy to bounce between them, and you're not having to wait that long when you're trying to change something more fundamental. It also makes it a lot easier to change things early on, because if you have these at the very beginning, you can't make changes and iterate as easily because you're having to break everything just to do it.
Yeah, here's an example of a big assembly that has all of these are done through feature scripts. So that thing would take a really long time to load and to make any edits, which was kind of a pain.
Yep.
You want to avoid that.
But also, if you look, not every single part is modeled in here. We have a bunch of spacers in assembly, a bunch of other small minor things. And so what we did was we moved those out to other part studios so that while this already is going to take a long time, it's not going to take even longer. So I know it seems like you're making a bunch of marginal changes for a very little game, but you really are helping yourself out in the long run by separating all the small stuff out so you can focus on your big parts, and then you can easily iterate on what you have to fix or change as the season progresses. So talking about how to create these assemblies, they are pretty easy, but we do things a little different than some teams. We try to model every COT or custom part that will be used except fasteners. So this has generated a lot of questions in the past, but the general idea is fasteners will drastically increase load time on basically every single assembly that you do, and they won't actually give you that much gain in return. What we try to do instead is we model very specific fasteners and very specific things. So for example, on this elevator where there's that pivot, we have modeled screws in there to make sure that they won't hit. But for example, the rivets that are going to go here, each one is going to be a bit of load time, and if we model every single one, we're going to add a lot of load time, but we already know those rivets aren't going to hit anything, so there's no real gain to put them in. It just makes our lives harder when we're trying to make changes to those. The other thing you want to make sure is that every potential movement is modeled. So whenever you're making an assembly, you have to be doing a lot of work to make sure that every single thing moves. So this arm goes up and down, the elevator comes in and out, the actual movement of this is modeled because you have to make sure that every single thing that you're doing is moving. Otherwise, what you're going to have issues with is something running into each other and you don't realize it because you didn't model every single individual movement that you could.
This can also help you catch like interferences. Like we had a robot a couple of years ago where like during the off season we were practicing and we like looking at the CAD, we realized that if we had built the robot the way that it was currently CADed, like this, it was for the 2022 game, so we had like the climber and then the shooter that was rotating. If we had built it, like the shooter would have rotated directly into the climbers and just like hit it every time we tried to shoot. So then basically if we just put it in the assembly, we may have just been like, okay, yeah, it works. But because we actually modeled how the robot would move, we were able to catch that stuff and avoid spending time like actually making that.
And then again, the other question.
When it says potential movement, does that include stuff like gear ratios for gearboxes inside of assemblies?
So we don't always model gears, but sometimes we do, and that's a pretty specific case. You want to model your gear movement whenever you have like a large or even a small gear that is actively near a bunch of other pins. So that can help basically just to make sure can you actually get wires through, because in your head you might think, oh, that gear's there, that's fine, you just move the wire over it and then it'll work great, but obviously you can't move the wire that goes to the gear. So making sure you have the more obvious movements modeled is very helpful, because you actually make sure that stuff like wires and all of those small things you don't necessarily always think about when designing are like this.
When you create your assemblies, are you referencing those sketches that you showed earlier
Yes.
at all?
Uh-huh.
So like those sketches, they like drive the assembly in some way?
In the Torch Studio, we will have like a giant reference sketch of the whole mechanism that we base everything off of. And then based off that, we will then like insert everything we made into the assembly and we try to add everything we can as like one giant block, and then try to like mate everything together, like put like the rotational mates and like what needs to move. But so like the assembly itself, we can't like see the reference sketch, but everything that's in the assembly is based off of it.
So there's no like direct link, like you can't do a design context or something like that to make the movement behave that way, but you can make sure everything that goes together goes together. You don't have a way to actually take a movement from the reference sketch.
But all the things that you validated in your sketch.
Are exactly the same.
Yes.
We'll keep the in the part studio. We'll keep the reference sketch like visible over like making all the parts. We'll like sketch on top of it.
Are there any other questions? So going off of that, you really, whenever you're doing any CAD for any kind of robot, the big part of FRC is constant iteration. You always want to make your robot better as much as you can for the entire system. So if you're doing that, you have to make it so your CAD doesn't break things if you change a single thing. So a great example of this is sketches. There are some sketches where you will change a single number and the entire sketch will go red and everything will cease to function. That is obviously not very optimal, because you have to spend all your time going through making sure every single little thing agrees with you, and that's a huge pain. So when you're doing that, you want to make sure your sketches are designed around use features. So that can be a mirror, that can be based off of a previous sketch. Your goal, at least for us, is to make sure that when you change one thing in your core reference sketch, the entire thing will change automatically. So we've had a couple elevators in the past where you can change one width dimension and the entire elevator will become that new width and nothing. That's obviously a pretty optimized thing because it was used as like a training exercise, but you want to get as close to that in season as you can, because that means that when you're having to change part of your elevator, change part of your intake, you can change it without having to then spend hours making sure your sketch works again. You also,
Because we do have a lot of like when people join for the first time and they're making their first CAD projects, they do usually just kind of like flood the screen with like dimensions, and then when like they try to edit anything, it just all breaks. So anything you can do to avoid something like that is very helpful.
yeah, like as you can see here, all of these hard number constraints that are basically saying the distance from point A to point B is this number is pretty rough when you're trying to iterate on something, because the instant one of those dimensions change, everything starts going haywire. And it's useful sometimes for your reference sketches if you're trying to do a more polished one for a mechanism or something like that. You really want to be trying to focus as little on those types of things as you can.
That's why the right side of that sketch has basically no dimensions. Because since we've used like use functions and made them like equal to the other side, if we change like one of these dimensions, the other side should change accordingly.
And then one last thing is try to have as little as possible directly based on something in that same sketch. Because what that means is that when you change something in that sketch, if it isn't the reference sketch, things are going to break. The only sketch where you really want to have stuff based on other things is the reference sketch, because that's going over the core concept of this is how everything should go together. But if you have that in different sketches, what you can get is that will start conflicting with your reference sketch whenever you try to make changes. So you really want to make sure that when you are designing something like an intake or pretty much anything on the robot, everything that isn't in the reference sketch is based on that reference sketch. Which is why reference sketches can get pretty complicated, but it means that as much of your CAD can be done in that reference sketch as possible. Any questions?
So how slide works. Essentially just like a giant like essentially just a giant list of files, of just a standard parts that everyone would use in FRC, like gears, pulleys, what motors. And having a team-wide library really increases your efficiency. Whether you like make your own, use a third-party one, like CAD is a great option that a lot of our students use, and it makes it very easy to find files from putting together assemblies. You don't have to like model like different. You don't have to like model individual parts, or you have to make your own gears. And probably more importantly, is that you can make sure that everybody working on the robot is going to have access to the exact same parts. Because if you just tell people like make the robot and they have to go find like the parts, like they have to go download the file from some website, people might go to like different sources, and then you just end up with a lot of people buying stuff like getting a lot of different parts that may not all work together, or some may be outdated. And this will just make sure that everyone's on the same page.
One of the things really cool about COTS libraries is that when you're using the COTS library, it basically means that whenever you need to change something, it's really easy to just go in and take a new gear or a new pulley or something like that and go in. The one thing that's kind of hard to do that for is like belts and chains because they adjust a lot, but generally our advice for that is don't bother modeling the entire thing because that has a lot of entities and increases a lot of load time. So instead try to come up with like a pretty basic mock-up of it so you understand where it goes, but you don't necessarily see every tube or every shaft. Next, we're going to talk about interference checks. So this is pretty much the best thing we like about CAD when we're doing our assemblies. So when you are doing anything, you've got to make sure that what you're doing isn't going to hit itself. So for example, right here, we have a gear going straight into a wheel, and they both are going to be spinning, and nothing is going to work. So whenever we're doing an assembly, we have to go through and make sure every single thing works. It doesn't even have to be the moving parts. It can be making sure that two plates don't go together, or making sure that a shaft doesn't go too long and so it starts getting into frame perimeter issues or stuff like that. We basically are making sure that every single thing on your robot is working well and doesn't hit itself. So a really easy way to do this on chip especially is just take a section view and you want to go really slowly through your entire robot. So you basically go in a little bit and you check all of your robots to make sure nothing hits. You go in a little more and you make sure nothing hits. And this can work for both robots and for your subsystem. So the really big thing that we emphasize for all of our subsystem needs is before you put what you made into 0 start by making sure it doesn't interfere with itself. Because if you put something into 0 and it interferes with itself, now the load time is larger in 0 but you're gonna have to redo everything you just did anyway. So double check that what you made works with itself first and go through, make sure nothing is hitting, and then put it into 0 and then do the exact same thing. This is again really important because when you have different subsystem leads working with each other on one big robot, it is pretty likely to happen that something is going to hit and something isn't going to work. For example, on our 2022 robot, we had a indexer plate hitting right on a climber plate because they didn't really talk to each other about who's going to take which holes. And so it basically meant that we had to, for our beta robot, we had to basically bandsaw down some gussets so everything would work, because otherwise we're going to have plates trying to be in the exact same spot.
And this seems like a very basic principle, but it happens to like pretty much everyone doing on-chip. Like this is not a hypothetical situation. This exact picture was grabbed from our team Slack because it happened last week.
Yeah. So this is a really common thing. We really have to make sure it's happening. I know it's a pain to like sit through and go through an entire robot and make sure nothing's hitting, but at least on-chip makes it bright red so you know where it is. But it is really important to know because otherwise you can get to assembly and you think you have this perfect mechanism, and then you realize that none of it works because 3 things hit each other in exactly the wrong spot, and now you have to start from square one again, or at least redo half of it. So go through step by step, little bit by little bit, and make sure nothing is intersecting, make sure nothing is conflicting, because otherwise you really are making it a lot harder for yourself. But then the really important thing is, especially if you have someone who's like in charge of CAD, or if you like have a group of people that are in charge of it, it's really great to have that group go through and especially focus on where subsystems come together. So if you can have like a couple people that decide, once we get everything in an 0, once we get everything together, it is my job or our job to look and make sure that nothing is going to hit, nothing is going to interfere, because that means when you get to assembly, you don't have any surprises going. This is interfering, this is bad, and then you have to take it.
Well, now we're going to talk about how to transition from CAD to manufacturing. Like right, you design a robot, but now how are you going to build it, right? So these are just kind of like the steps we take to do this. So first off, design students label each part inside of the CAD software. You can label this however you want. For years, we've just been doing this system. But like you guys remember earlier when we had the different subsystems, we had like 0000, and like 00100, and like so on. But like basically 100 would be our drivetrain, 200 would be like the shooter. So for here we've got like 1678, the year, this is 2017, and then the part numbers. This is like 101, that is 100 is the drivetrain, so drivetrain part 1. And then we put who designed it, who's going to machine it, how much we need, and like the status of the part, whether it's like in the design process, whether it's like it needs like just a sketch for like the machinist, whether it's being machined, or whether it's complete. So we just use our own spreadsheet to track all these different parts every year. And we use CAD for part drawings, DXF files if you're using like routers, STLs if you're doing any 3D printing, and more.
And then one really important thing about this is off to the right, there's another column that basically asks for details. So this is really useful because even before they get the part drawing, if it's a mill part or a lathe part, or before they like start looking at the part in the CAD software for running a router, they can basically look at it and say, okay, this is the stock that I want, this is the type of aluminum that I want, or something like that. So basically, when you put everything in this spreadsheet, it enables everyone to see what you are doing with each part. And also it's really great because even if it's the end of the day and you went home and you forgot to check if a part was done, you can look at the spreadsheet and say, oh, cool, they did make it, or oh no, they didn't do it, we'll have to do it next week.
Yeah, this is just our like super specific way of doing this. But what we're getting at is that communication between whoever is designing and fabricating, whether they be like the same person, different people, that communication is really critical. Like there have been times where like the designer will make like some mistake, and the machinist will come back with like just the wrong part, and then no one's happy. We have to do it all over again. And it's just, basically, you just want to make sure that you have a very transparent like relationship between who's designing, who's building, and who's making all the parts.
Something that we like to say is the designer's job is not over until everything's together. So basically, just because you put a thing into CAD and you're like, this is going to work, you are still responsible for making sure that it gets machined properly, that it's getting post-processed properly, they're reaming it to the right size, they're deburring it well, stuff like that. So it's really important to have something like this for its core, but also make sure that your designer is actively taking steps to make sure their parts are working. So you can't just sit on your toes and say, this is going to go great. You have to make sure that this is actually getting talked about with your machinist. The machinist knows what they're doing. If they need help, you can help them and stuff like that.
So part drawings. These are important. These are one of the most important parts of like the communication between design and hardware, because it enables fabricators to make parts without like necessarily having CAD open, and you basically just make a blueprint that needs to be as clean as possible while sharing all the necessary information. And very importantly for part drawings is you want to define everything from one corner to keep everything consistent. Like if you just have like a giant metal plate and like a hole in the center and you say how big the hole is, like they can't make that because they don't know like where the hole is. So you want to like define it off like you want to basically define everything off one point so that they know exactly like how far from the top and side it is, and then you can like define everything based off itself. But you want to make sure they know everything they need, and yeah. So here are a couple of examples of part drawings. We crossed out the names just to kind of respect the privacy of the people who made them. This is just our custom template that we use, but we in Onshape there's like a part drawing function where you can essentially just place in sketches of your parts and then add dimensions to them. So the way we do that is like you can see we base this hole off at this corner, then we base like where these holes are off this, then where this basically we try to make it as clean as possible despite this part being like very overly complicated with a bunch of different holes. And we try to just keep it organized by saying what part it is, how much we need, what kind of stock it is, who made it, again, for the communication process, so that if anything goes wrong, they know exactly who to talk to. And then we also have an example of like a shaft, where we want to make sure that they get every view that they need to make it. So like for a shaft, they don't need an isometric view like this. It doesn't really give them anything. What they need is a front face view so that they can see how big the part is. And if you're going to add like snap ring or like U-ring grooves or anything, you need to like model out exactly how big those need to be.
And then also something that'd be really useful is, it seems a little scuffed, but if you see right there, there are like two little word notes. It says all holes are 0.91 and cutouts are 0.5 millimeter ending. So that's really useful for machinists because a lot of the time you can like sit there and you're thinking about it, and if it's in like a millimeter, it'll just show a like weird decimal. The machinist is really good. So even just writing down with words what you need something to look like or how you need something to get done can be really useful communication because you're basically just letting them know how something needs to happen. And then as Sim said, having this name is really important. One, because when they're done with the part, they need to know who to give it to and make sure everything's good. But also sometimes a designer is going to forget a dimension or they're going to forget something and they're going to need, the machinist needs to know who they can talk to so they can actually make sure this part gets built. And so it's really important to have that there along with all of the other information. So if you get the part number, they know like, okay, this is the assembly bin to put it into, or the quantity is also really important because they need to know how many they're going to make. So trying to streamline everything with an official like system of communicating is really important. So not just having the designer take initiative, but having a structure that enables people to know what they are doing and how. So you don't have to spend the entire time spelling out each of the measures.
And cleanliness here is like very important. You see how like every single measurement is just placed on top of one another. If you were to like start making those like the left or right, just by like click, like okay, I'm gonna dimension this, click off, dimension this, click off, without like really paying attention to where those dimensions are, it just becomes like really messy. Lines start crossing each other. You just don't want like this. You don't want like it to look like a giant cloud of smoke over your part of just dimensions, right? Because people have to read this and they need to know exactly what you mean, like when you put in a number.
And then one other thing, this isn't really easy to show a visual for because it's all done with like small letters, but if you're giving a part for like a router or something, it's really useful if you name the DXF with everything that person needs. So if you have like a router part that you need to get made and it's made out of 1/8" aluminum and you need 3 of them, it's really great to see the part number, the quantity, the stock, and the thickness because then the person who's running the router knows exactly what they need to do off of only that DXF and they don't have to go around taking in the CAD or finding you to ask and say, oh, this is how I need to cut. This has happened with us in the past where they've either asked for the wrong thickness or the wrong like type of aluminum or something and it causes big problems. So you really want to make sure you're stating clearly what that is so the machinist isn't guessing. So if you have any questions, feel free to send me an email here. We also, I believe, have a bunch of Citrus emails if you want to send anything there. And we are happy to answer any questions now or online.
Yeah, thank you all for attending. I'm hoping that you gained something from this presentation. And yeah,
Any questions?
we'll stick around for a few minutes.
So any questions?
Specifically, you could probably want to search parts. You guys trying to keep them like separated, especially in your sub assemblies. But also like for some sketches, like integrate them. So if you want to change one value, the whole sketch adapts to it. If you're mounting, for example, an intake onto an elevator, right? That mounting joint, say you want to change the dimension of that, would you keep that individual in both sub-assemblies, or would you make that like an integrated part between both of them that you just
So
change?
the way we would do that is if it's something mounting onto something else, you leave all of the mounting features in that. So for instance, if you're doing an intake, the intake has all of the intake mounting features. And the way you normally do that is you take part of the reference sketch for that. So like if you know where the elevator tube is that you're mounting to, you take the reference sketch for that, anything around it, you take that sketch specifically, and then it's pretty much all the information you need. And then if there are any problems, you find them. But normally that works out pretty well. And you just have to check.
Obviously, talk with if the intake and elevator will be done by two different people, make sure they both like, know exactly what's happening, so that one of them doesn't be like, okay, I want to mount like some other really cool 3D printed part on this plate that I'm not using, like the intake plate. That's just communication.
Yeah, it's also with the 000, like starting from sketch. Like you are going to mount in this area, don't touch that. Anything else? Your time is usually going to be pretty high, regardless. If it's a simple robot, you're probably going to spend a lot of your time iterating. If it's a really complicated robot, it's going to take a lot of time to make anyway. The answer, I don't really know a number for. It's very large. I recommend trying to make sure that, especially if you're like, try to make sure that you're giving as much labor away as you can. So don't be like spending all of your time designing everything in the subsystem. You can design the overall architecture, maybe a couple key plates, and then leaving the smaller stuff.
You do want to make sure you have time to actually, like at least a few weeks to actually manufacture those things.
But the way we recommend doing that is basically have one mechanism be manufactured. So basically have all of your router parts for like an intake get done and then your router parts for something else, because that means that you get your intake done and your other thing isn't going to be done yet, but it could be done anyway. So you might as well have something done, especially for electrical and software to work with. It's not really something we talked about as much in this, but it is really important to realize that on most teams, design is the major job. So you really got to make sure that you are moving as fast as you can to get electrical something to do, your software team something to do, your driver something to practice with. Because any practice time is better than no practice time. And I think practice with the drivetrain and intake, that's better than sitting on the cube.
Yeah, we try to get the drivetrain out almost like as quickly as possible, so that the driver at least has like the ability to work. And it's the software can work there, though it's already
So I'm just multiple people on a subsystem team. How many people go on a subsystem team? How frequently do they meet to work on their subsystem?
So we have one person directly in charge of the subsystem. At the beginning of the year, we kind of split up all of our hardware teams into working on prototyping, and after that, it kind of moves away. So normally you'll have like one person in charge of a subsystem, and then maybe 2 to 4 newer people working on it with them. But
that really depends on team size.
it depends on team size a lot of the time.
How many there are.
And the really important thing is try to make sure that you're getting it so that new members are cool. Because obviously better members aren't going to be around forever, so it's really about trying to make sure that you can pass on knowledge.
Usually when we're just like working for that member, we go into like the launching tutorials.
Actually, someone's okay.
They're pretty good.
Anything else? Thank you for coming.
Okay.